watching two people outside my window. They came out beautifully wearing face masks and then took them off so they could smoke, and they're yelling at each other. But they are about 6 feet apart, so I guess that's good. Any questions? We didn't get through as much Android stuff as I wanted to yesterday, but it was really just kind of a teaser to let you see some of the stuff and get you started. But it's really scraping the surface. There's a whole lot more, but I think you've got enough to get in and make sense out of the documentation and so on. And if you're looking for something to play with over the summer to sort of keep your programming skills sharp, that's not a bad area to explore. Potentially marketable, and definitely, you know, a doorway to a much wider world of programming, interacting with hardware, and, you know, dealing with a more modern framework. Is all good stuff. All right. I haven't written the final exam yet, so I haven't put together a study guide for it yet either. Our final is limited to 60 minutes for some administrative reason. So I'm still debating whether I'm going to spread it out over 2 days or just do a 60-minute final. But you will definitely have a final exam this coming Monday at 10 o'clock. But I'll decide in the next 24 hours whether we're going to have a Monday, Tuesday, or just a Monday. And I'm leaning towards the same format as last time, where it'll be a Canvas quiz, and you'll be writing code or writing answers and then uploading them through Canvas in the quiz area. And we can do a review on topics in a bit, but I wanted to just kind of for fun, I wanted to take a look at some source code from Java. Monday, 10 o'clock. And I think that should be on Canvas. If it's not, I will put it on Canvas. Alright, so yeah, at your usual meeting time, and it will be on the 15th. So Java is you know, the Open JDK, which is what I've been running, is open source, right? And open source, you know, has been a thing for a long time. It has different meanings, but the main idea of open source, the most common idea of open source is basically, you know, the design or the source code or description or specification of something is publicly available, right? It doesn't mean you can't sell it. Okay, in some cases, an open source license still allows people to sell it. For example, Red Hat sold you know, commercial versions of Linux when it first came out, even though Linux was open source. But usually it's more about restricting what people can do in terms of locking down information. So if I publish something open source and somebody else is allowed to redistribute it, they have to keep the open source license intact, right? They can't change it to a proprietary license. And there's a few categories of specific behaviors you can allow or disallow. For example, you can say you can use this, redistribute it, etc., but you have to name the original author when you do that. or you're not allowed to use this for commercial purposes, or you're not allowed to make modifications to this. Okay, but it's putting it out there in a way that's very open, presumably, you know, to let other people look at it, learn from it, and then perhaps, you know, build from there. And so OpenJDK is an open source version of Java, right? JDK is the Java Development Kit. I don't know if we've actually talked about that, but there's two branches of Java stuff you'll find. JRE is the runtime environment, JDK is the development kit. If you're just running Java code, you just need the runtime environment, JRE. If you're developing like we've been doing, you need the development kit that gets you things like the javac command, the jar command, the jdb command, and so on and so forth. So let's look at some source code. So you can download this as a big zip file, and it's basically, you know, a bunch of .java inside here. So 17,000 .java files, and this is pretty much the totality of the base Java package. So I've extracted a few of these. I didn't extract everything. But let's look at the string class. So the string class represents character strings. All string literals in Java programs such as ABC are implemented as instances of this class. Right? And you've seen this before when we look at the Java documentation. The string class represents character strings. All string literals in Java such as ABC are implemented as instances of this class, right? All of this Java documentation we've been using throughout this quarter is generated from the source code, right? And this code starts with a /** tag, so this is stuff that the Java doc command, which we looked at one day, will ingest and turn into that documentation. And so, you know, as we've been trying to do ourselves, the beginning of this class has a comment block that describes the class. What does the class do? Represents character strings. Strings are constant. Here are some examples of how strings can be used. The class includes methods for doing these things. The Java language provides special support for string concatenation using a plus sign. Unless otherwise noted, passing a null argument to a constructor will cause an exception to be thrown, right? This is general information that somebody coming to this string class and wanting to know about it could find useful. Okay, so when we talk about putting a comment block in the beginning of your class declaration, right, these are some of the things that one might include. And then, you know, the names of the people who wrote this, so I keep asking you to put your names into your code. That's a place to do it. And I'm not saying you have to use, you know, author tags and JavaDoc and all that kind of stuff, but the information itself, right, it's useful to have in here. And then here's the declaration of the class itself. And, you know, it's got a character array called value. So our strings actually character arrays inside? Don't know, and frankly, we don't really care, because we don't access the individual elements by saying, you know, string name dot value bracket such and such. This is handled inside the class itself, which is why this particular thing called value is marked private. Coming in from outside, I cannot do anything with this. I can't look at it. I can't change it. There's also a thing called hash, which is an integer. We'll talk about that in a little bit too. Alright, there's some constructors. There's another constructor. There's another constructor, right? And each of these constructors, there's a paragraph here telling you what this method is about, right? What kinds of things it's trying to do, and then detailing all of the arguments. What's the type of argument? What's the purpose of that argument? What does this thing return? Can it throw exceptions? Here's the equals method. And equals just checks to see if this, the thing that you're calling this equals method on, is exactly the same as the object that you passed in. And if it is, it returns true. It's done. Doesn't have to look any further. Otherwise, what does it do? It goes through a loop. It finds the length of the string that it created from the argument, right? And then it makes a decrementing loop down to 0 and compares character for character. And if the characters ever differ, it returns false. Otherwise, it returns true. Right? This is the low-level stuff. This is what's going on inside. We've got this nice clean class called string. We can make two things of type string. We can say thing1 dot equals parentheses thing2, and it tells us true or false. But inside, what's happening? It's going through character by character and comparing them, right? And so that's, you know, encapsulation and information hiding. We don't get bogged down in the details of how that works. It's happening for us, and it's making this string class usable, right? And if somebody decided to do something differently in here, right, as long as the equals method still does this stuff, right, it's not going to matter to us. So this code can be modified and enhanced and sped up and so on and so forth. And it makes no difference to the people using this. Alright, there's the compare method, which, remember, sorts two strings and tells you which one is bigger or smaller than the other. Well, it tells you if one is bigger or smaller than the second. So look at the two lengths, take the minimum length, right, because that's how far we're going to compare characters, and go up to there, grab the character from each of these strings, and notice how does it find the ith character? It uses the character at method. It does not go in and say, you know, s1 dot value bracket I. Okay, it could, but even within this class, we're trying to obey the notions of objects. We're trying to use this encapsulation. The string method has a character at method associated. The string class has a character at method associated with it. And so when we want to get the ith character, we're going to use character at. And then, you know, if we decide we're going to store these strings differently from an array of characters, we don't have to look around and find every place that we used, you know, s1 dot value bracket I and change it. Right? So this use of methods to access information, the obeying of information hiding, is permeated throughout all levels of this. Okay. If the two characters are differ, convert them to uppercase. If they're different, convert them to lowercase. And if they're still different, then return the difference in their character values. Right? Otherwise, if we go through and the first n1 characters are the same, return positive, negative, or 0 based on which string is longer. If they're the same length, the strings are exactly the same. If the first one is longer, then this will be positive. Right? So if we want to know what the value of that integer is that's returned by compare, we can find that in here. And sometimes it's the difference in character value where the first mismatch occurs, or if the strings are the same up to a point, and beyond that point one string ends, the other one is longer, it's the difference in the lengths. right? And how do we convert something to lowercase? Right, and here's the documentation for the to lowercase method. All right, converts all the characters to lowercase using the rules of the given locale based on Unicode. Examples of lowercase mappings are in the following table, and here's a table built into my documentation showing how case conversion happens in particular locales, Turkish, French, and so on. There's some images in there, etc., etc., etc. All right. If we don't have a locale defined, that's an error. Otherwise, I haven't looked at this yet. We'll basically loop through, check if there's any characters that need to be changed. Here we're getting that character because we want to access that particular element. And I don't know what all this stuff is doing, but it's basically a wrapper around the to lowercase version of the character class. All right, so this is, there's the toString method for a string. Return this. Why? Because we don't have to do any conversion to convert a string into a string. So there's a one-liner for toString. Let's look at an object. So remember, everything is an object or an extension of an object. So general little boilerplate code up here: do not alter or remove copyright notices or this file header. This is under the GPL, the GNU public license. And it reminds you should have a copy of that license when you got this software. If not, etc., etc. And then the description of an object, the root of the class hierarchy, right? Every class has object as a superclass. And so every object implements the methods that are in this class, either because they inherit them from object or because they override them, like toString, for example. So what does toString do? Return a string representation of the object. In general, this returns a string that textually represents the object, right? Which means usually you're going to override this. But if you don't, what does it return? It returns the name of the class, an @sign, and then an integer expressed in hex. Right? We've been seeing this since week 1. If you just do a print line on an object that you haven't written a toString method for, you get the object's class name, @ and then some weird hex number. Well, that hex number is what's called the hash code of the object. So what is a hash code? So public int hash code semicolon. The description of it is return a hash code for the object. Supported for the benefit of hash tables such as HashMap. And there's no description of this public native int hash code. This means the code for this is not written in Java. It's written in basically the machine language of the Java virtual machine. That's what the native keyword says. So finding the hash code corresponding to an object is a lower level behavior than we can easily do in Java itself. It's really kind of going in and trying to figure out the DNA of this thing in some sense. But remember, when we talked about hashing in 224, what was the basic idea? If we wanted to hash a string, we might do something like, add up the ASCII codes for each character and then reduce it modulo whatever, right? And we basically take an arbitrary string and we reduce it to an integer. Or we could have a binary tree, and if we wanted to make a hash code for that, we could add up the ASCII codes for the data in each node, multiply that by the depth of that node, and either square it or cube it based on whether it's the left or the right child of its parent, and then take that whole sum and reduce it modulo, a zillion and one, and we end up with a number that more or less is unique to that particular tree. Now, it's really not, right? There's a lot more strings than there are integers. There's a lot more binary trees than there are integers. But the idea is that for a small set of objects, it's pretty close to one-to-one, right? And the idea of hash codes was we would use it to decide where in an array we were going to store an object, so we could quickly retrieve things. So hash codes are part of every object in Java, and their implementation is done in this lower level area. All right, and there's the equals method, and look at all this documentation, right? So indicates whether some other object is equal to this one. Implements an equivalence relation on non-null. What's an equivalence relation? It's reflexive, symmetric, and transitive. Okay. A is equal to A. If A equals B, then B equals A. And if A equals B and B equals C, then A equals C. Satisfying those three properties means that you have a transitive relationship. And what's the actual code? It just returns whether the object that you're passing to this method is equal to yourself. All right, and there's a clone method. Which can be used to create a copy of yourself, and that's also a native method. That's implemented in the lower level of the language. All right, what else we got here? All right, here's the scanner code, 2,600 lines. So when you're scanning and you get a stack dump from your execution, and it shows you all those weird line numbers where something went wrong, and sometimes you see scanner.java : 1638. Those are lines in this file, right? And you can come in here and you can actually see what the actual statement was that caused a problem, right? And so again, lots of documentation in the beginning for the class itself, right, including the obligatory Dr. Seuss. All right, here's the HasNextLine method. And most of this is just pulling up internal information, right? It's ingesting from your source and caching those results and looking into that to say, is there's something available. Here's the next line method. And this is heavy modularization. None of these methods are all that long. Right? For all the times that we use NextLine, it's just a handful of statements, and most of the stuff doesn't get used. There's probably one statement in here that we use the majority of the time, but that's because this method is comprised of calls to things like get cached result and clear caches and so on that are themselves relatively few lines of code, but call lots of other methods, etc., right? So you don't want to look in here and see that a method is 5,000 lines of Java. If it is, there may be a way to break it into pieces, and particularly if it's part of a well-written class, a well-designed class, right? It should be doing things that are similar to what other methods are also doing, And when you have two or more methods doing similar things, those similarities can themselves be put into other methods or other pieces or maybe other classes, right? So this is interesting code, I think, to look through just for kind of samples of code. And you notice not a whole lot of comments inside the code itself, right? Because these methods are fairly small and they're really, really well documented up front. But search for the pattern up to the end of the input. There is some commenting in here, at least breaking up what the different major sections are, right? If we have a result, then we're going to cache it, and so on. Linked list. I don't think I want to go too deeply into here. But it's got nodes stored in here. It saves the first node, it saves the last node, it saves the size of your list in an integer. And the add method, for example, which should add to the end of the linked list, well, it just calls link last and passes the object that you want to add. And link last is something which adds to the end of a list, but is somehow more general, and so on. Here's a remove method, right? And it's a good old for loop. All right, one more to look at. Let's look at the hash table. Right. So what is your hash table? It's an array of these entries, right? So when we implemented hashes in 224, right, we said we're going to make an array, and in this array we're going to store our data, but we're going to use a hash function to tell us where we should store our data in the array, and then we're going to do some special things for handling collisions and so on and so forth. So this is the array of objects that is the hash table. So what does the get method do when we say get an object? So here's our hash table. Let's find the hash code on the object we're looking for. Okay, let's shrink it down to 31 bits, right? So we AND it with this bit mask, which clears out the most significant bit and retains the other. So it's a 31-bit index, and we reduce that modulo the length of the array. Right, which takes our object and gives us an entry, an index somewhere between 0 and the length of our array minus 1. And then we basically search through to see if at that location we find our item stored, and if we do, we return its value. And if we come out of this and we haven't found our item, then we return null. Okay, this was one of your ODPs, right, in 224. So I mean, this is I'm doing this partially to try to promote this idea that this really isn't magic, right? Even though magical things come out the other side, this is all just code. All of our smart appliances and the wonderful things we can do online and all of that stuff, it's all just code. And it's code that is, at the lowest level, not terribly complex. It's how these pieces are put together and organized and used to build up larger pieces. That's where the complexity comes in, right? But all of you are completely capable of, you know, understanding and writing this kind of code. And there's nuances here with generics and you know, things like that. But the programming aspect, the algorithmic aspect, this is stuff that you're all well versed in, right? And all of this gets turned into, you know, Java, which is Android, which is smartphones, which is, you know, everything that smartphones are today, good, bad, and ugly. And it's all just code. So, I don't know if that's a pep talk or just a synopsis or what, but I don't script these things out ahead of time. All right, so if you want to mess around with some of that stuff, that's another fun thing to look at. If you've got time over the summer and you want to brush up on things, and you know, you can modify this stuff. If you want to make your own version of a string class, you know, you could copy the source code for string and call it, you know, my string, and make some changes to it and play around with that. If you want to extend the linked list class, or you want to dig deeper into the scanner class. And sometimes when you start tracing these things down, like what happens when I open a scanner on system.in, it feels a little Alice in Wonderlandish, like you're never going to get to the real heart of it, right? You just keep tracing methods that are calling other methods that are inside this class, which create something from that class, which calls this method, and you wonder, you know, where does this actually happen? And usually at the lowest level, you're going to end up with some native method, right, which is implemented in lower level code, and that's where, you know, something talks to the operating system and says, hey, you know, somebody pressed the enter key, what should we do about this? If you do this in C, what you do is you come down to, you know, chapter 2 functions. So, you know, like the read function from manual page section 2, these low-level things. But if you dig into the code for these, what you'll usually find is that these are being executed with software interrupts, right? Something is being set up, register values are being loaded, memory is going to be organized in a certain way, and then a software interrupt occurs, an exception, right? Because when an interrupt occurs, the operating system kicks in, and it kicks in privileged mode. And it will look at what's being set up in memory, and it'll say, hey, somebody wants to read from this file, right? And it will make sure that permissions are appropriate, and if so, it will actually interact with the hardware. So now you're down to, like, typically assembly language drivers that are doing the kinds of things we do in 270, right? Setting up register values and you know, raise this from a 0 to a 1, and now you know, this piece of hardware that's connected to the network is sending us bits that are coming in a packet. So you'll take classes down the road on operating systems and system programming and things like that, and you'll see some of these pieces in a lot more detail. But you know, this is another fun, useful exercise, is sort of trying to get yourself a continuous picture from top to bottom of something, right? Not the whole of Linux or the whole of the JVM, but something like what happens when I say, you know, print this character to my screen. How does it end up, you know, right here? How did this letter B end up right here? And if you want, you can go even further. You can say, you know, once my program running on my laptop was told to display a B here, how did that B pop up, right? What's happening at the hardware level? What is this thing that I'm looking at, this screen? Is it a series of little tiny LEDs? Is it an electron beam sweeping across, lighting up phosphor? Is it magic pixie dust? You know, and how does this image of the letter B appear, right? It's a few bright dots surrounded by non-bright dots. And you can break this down as far as you want. And sometimes that's cool to do. All right, none of which will be on the final exam, by the way. But that's stuff you can dig into. All right. So any questions or comments? Well, I look to see if I have a final exam study guide. So I got to look this over, and I'll post something up on Canvas tonight, and we'll talk about it tomorrow. But again, same thing as the midterm, right? You can basically expect to be writing some code. You can expect to be analyzing code. You can expect to be modifying code. Okay. Sometimes I'll ask you to do an entire program. Sometimes I'll ask you to do a method. There might be short answer questions. There might be conceptual questions. Yeah, I'll go through this and write something up and post it, and we can talk through it tomorrow. We got 9 minutes left. I was thinking about talking about Dijkstra's algorithm because we did not get to that in 215 last quarter, and I meant to do it this quarter. I'm not going to do that. All right. If you got questions, let's talk about it. Otherwise, I'll let you out 9 minutes early today, and we'll just we'll wrap up tomorrow with going through a list of topics to think about for the exam. But I'll be here, and then I have office hours at 11. Otherwise, enjoy the day, and I will see you next time.